Okay, this is going to be a video about how DC motors work. The first thing we're going to note here is that when a wire that's passing a current is in a magnetic field, it's going to get a force from that magnetic field. You can view this as just a force that's acting on that moving charge or the current, or you can view this as an interaction between the magnetic field that was created by the moving charge and the magnetic field that already existed. We're going to start by just focusing on a moving charge, a current that's experiencing that force. Let's say, for example, that I have a wire. I'm going to put my wire going straight up in the page like that. Put an arrow in my wire to show the direction of the current. And then let's put this in a magnetic field. Oh, it should be noted that the force here that's going to exist on this current carrying wire will only exist if the magnetic field and the current are not in the exact same direction. If they're in the exact same direction, then this won't work. So there's a right-hand rule that's going to let us see the direction of that force. The rule says, just the magnetic field here would be going across. Remember, a magnetic field shows the direction that a north end of a magnet would point, so the north end would be repelled by this north and attracted to the south, so it would want to go to the right. So what you want to do here is you want to put your fingers in the direction of the current flow, and then you want to put your palm in the direction of the magnetic field. So I'm going to draw this hand here. This is a little bit hard, but just imagine those are your fingers, and then your palm has to be on this side because it's going in the direction of the magnetic field. So if you do that with your own hand, what you're going to see then is that your thumb, I'm just trying to draw them in here without being too confusing, is going to end up going into the page. So try that. Put your fingers going up with the current, right along with the arrow that has the eye on it. And then make sure that your palm is pointing in this particular example to the right, and then your thumb should be pointing straight into the screen. And so that would be the direction of the force experienced by that wire. And just try another one here. Let's say that we have a current that's coming out of the page. Why not? That's our current carrying wire. And this time we'll have a magnetic field. I'll put the south on this side and the north on this side. Doesn't matter. So this magnetic field is going to the left. So here you're going to put your fingers out of the page, so coming directly out of the screen, and then turn your palm so that your hand is, so that you could high-five somebody to your left, or so that your palm is pointing towards the left-hand side of the screen. Your palm is pointing this way with the magnetic field. And then what you're going to be able to see when you do that, hopefully, is if you extend your thumb here, your thumb would be going down. And so that gives us the direction of the force. You can keep practicing this. There's more practice in the book. I'm gonna move on. So if we use a couple permanent magnets, north and south, and I use red and green just to show some differences in the loops here, and then you use a funny wire that seems to be colored red on one side, and then when you hit the midway point it's colored green, and that it's not really different colors. I'm just doing that so that you can see the difference between the two sides. And then you attach those things, just for right now we'll just attach them directly to a battery. And again, in all my things here, I'm just doing positive current flow here. So I'm just gonna treat it as if the current's coming out here and coming back in down here. So let's focus on the red side of this first. We've got a current that's going up. We have a magnetic field that is going from left to right. So if I put my fingers going up, my magnetic field, my palm to the right, then I'm going to see that my force acting on that is going into the page. And so that would cause this motor to try and spin so that the red wire is going down. Now if we do the same sort of consideration on the green wire on the left, then we have a current that's going down, a magnetic field that is still going to the left, to the right, I mean, from left to right. So if I put my fingers going down, or sort of towards the bottom of the screen, and my palm going so that it's going from, the palm is on the left-hand side or right-hand side? Right-hand side, sorry. Then your thumb will be pointing up, showing that that force is pointing out of the page. And so what we've done is we've created a situation where we're pushing down on one side of this apparatus and up on the other side of the apparatus, or I guess really to be more accurate, into the screen on the left-hand side and out of the screen on the right-hand side. And what that's going to cause is that coil or that wire to rotate. And that's basically what we're trying to do with the motor. The problem is that sometime shortly later, if we imagine that this whole apparatus gets to spin around, which way would it spin around? Spin around down on that side and up on that side. Then sometime shortly later, what's going to happen is you're going to have basically the same apparatus, except the red wire is going to be on one side now, and the green wire is going to be on the other side. So for a properly functioning motor, we want this thing to just spin around and around and around, keeping going in the same direction. As I've set it up here, it would be going counterclockwise. This is counterclockwise. But the problem is, if I spin this, then if you remember, I attached, if you look at the above diagram, the positive side here, and that's attached to that, and this is still in the same permanent magnetic field. This isn't changing. So what's happening now is that the current is going out of the battery and up on this side, and then over to the green side, and down, and then back into the battery. Now let's just think about the direction of these forces. Current here is going up, the magnetic field is going still left to right, and so if I put my fingers going up with the current, my palm, so that I could high five somebody to the right of me, then what I will see is that my thumb is going down into the page. Alternatively, on this side I have a current that's going down, get a magnetic field going across, and so if I put my fingers in the direction of the current, my palm is still to the right, or this is an awkward one for your hand, but you'll see that your thumb is pointed up, or out of the page. So what happened here was that I had, let's go back and sort of sneak a peek at this diagram here. I should go with black so I'm not confusing. Here on the left I was going in, and on the right I was going out, and that created my counterclockwise rotation. Now that this thing has spun through 180 degrees, I have my force on the left coming out and my force on my right going in. So what that's going to mean then is that this wants to stop going like that and come back around this way. So if this motor was really set up this way, it would swing one way and then it would swing back, and then it would swing one way and then it would swing back. And I think you could probably think of a situation where that'd be useful, but that's not what we're trying to do. We're trying to get the motor rotating in the same direction all the time. So the trick to this is that we want the battery to switch its direction. We want this current to be going in a way that allows it to continue to rotate in the same direction. So we want to switch the current every 180 degrees. The way that we can accomplish that is with something called a commutator. Imagine a commutator is essentially like a ring, but it's broken at the top and the bottom, or it doesn't matter, but two locations. And then we, instead of using a normal, like say alligator clip or something like that to make this connection, we use something loose but that can maintain good connection even though it's not directly connected, like a brush. So these are this is called the commutator, and this is called the brush. If you imagine, if you're holding your pencil, imagine instead of gripping it that you just put your two hands flat and you held your pencil by simply pushing your hands together, and that would be like these brushes sitting on the ring of the commutator. So as it spins, the let's say the red brush would be attached to this side, and then later, as this piece of the commutator came over to this side, the red brush would switch and connect on the other side. So you could get the battery sitting in the same direction all the time, even though the wires are switching back and forth, are rotating back and forth around. And what that does is that switches the current to allow you to maintain that direction with the motor. There's still two problems with this, or there's still a problem with this, and that is that when that loop that you've created, and this is sort of an awkward diagram, but I'm going to still try and do it, is at 90 degrees to the magnetic field, you're not getting any, there's no, as they would say, torque, or there's no there's no torque or rotational force. If we imagine, let's just put the current in going this way, and it'll be coming out that way, then, and the magnetic field is going this way. Then here, I'm just going to go really quickly. This is going in, this is going over, so this would be going down, and this would be coming out, and this would be going over, so that would be going up. And those two forces, you can see, are working directly against one another, and so basically there's no net force in this direction. And so we get no spin. And what that would cause is, if we look at our motor here, when it's in position 1, it'd get a good force. And when it's in position 2, it'd get a good force. But when it was halfway in between, it wouldn't be getting any real rotational force at all. What that means then is that the motor would spin inconsistently. It would kind of go fast when it was at 90 degrees, or when it was flat, and then when it was straight up and down, it would slow down, and then as it went back flat again, it would go fast. There's two basic strategies to try and get past this. One, and probably the simpler one, I think anyways, is to use an armature. Here you can see the coiled loop at the top and the bottom, and this is a nice picture of a commutator right here, and you can see the brushes that are holding it on either side, so that as it spins, it switches the current. But the armature essentially is a temporary magnet, like iron or something like that, that's placed in the middle. This is something that when a current is passed through those wires, it can actually create more of a magnetic field than would have been there otherwise, so it actually sort of makes it stronger. But what's also important here is that if it's a metal, then it's probably fairly heavy, and if it's fairly heavy, as it spins, it's going to have inertia. Remember, inertia is the property of matter that means that matter wants to keep on doing what it's already doing, or it wants to keep spinning in this case. So as it's at, if it's flat and it gets a big push, because that's the way that this motor is designed to work, then as it hits that 90-degree angle where it's not experiencing any meaningful force, the inertia of the metal, or the fact that the metal wants to just keep on spinning, will allow it to carry through that part and then get back to the point with force again. Basically, it adds some weight to it, and that weight allows it to keep spinning even if the force is a little bit inconsistent. In this particular type of motor, we get back to what I said all the way back at the beginning, which is that the interaction between the wire and the magnet can be thought of either as the magnet just adding a force to that current carrying wire, or it can be thought of as an interaction between the magnet that is on either side of the motor, or and the electromagnet that is that's created by passing the current through. Let's just look at that idea quickly here. So let's say, for example, I have a piece of metal and I'm going to wrap it as a solenoid and then bring my wires out and attach them to a battery. Well, the rule for the magnetic field in a solenoid is that if you wrap your fingers in the direction of the current, you're going to get the direction of the magnetic field. So let's just pretend the current is going across the front of this. And if I put my fingers around it and I hold it with my fingers coming across the front, I can see that my thumb would be pointing up. So this would be a north and this would be a south. What that means then is that this north would repel and attract, and this south would attract and repel, and that you can see would create the rotation of the motor. If you try and carry this through and you don't change connections, then sometime later, when that north is down and that south is up, because we didn't change the battery, we kept everything the same, then what you would see is that you get 180 degrees around, and then you start getting pushed backwards again the way you were. And so this is another one of these motors that if you didn't do something, it would rotate down and then rotate back up and then rotate down and then rotate back up. That's why we still switch the current. We use the commutator and the brushes to allow the current to be switched, and that allows the inertia of the armature to build up and create an effective spinning motor. That's sort of half the battle. The other approach here is to use multiple loops. So if we again take our original motor and we say it's good in that direction, but we're having a problem with it when it's going like this. So what you can do, as you can see in this diagram over here, is you can just basically combine these two situations so that at no point is one of the loops, or is the only loop, at 90 degrees. This is a little trickier because you're almost going to want to, you have to control the current a little bit more carefully. You can imagine in this situation, as I've drawn it here, that you would have a 4-sectioned commutator that is designed to connect the current here or here, depending on what it is, where the motor is in the spin. What you can see in a real motor is that you can have a lot more loops with a lot more connections in a well thought out way, and in a real DC motor combine that with an armature to create inertia, and that's how you would make a real DC motor that would effectively convert electrical energy into some sort of spinning mechanical energy. So that's all for this video. More to follow.